So expect a quiz on Friday. You know that, right? Yeah, simply just R2, R letters. And there's something due next Friday. Yeah, there's something due today? No, Friday. Okay. Yeah. All right. Let's get into the ADC structures. First, we have to go through OpAmps because the comparator is one part, critical part of the entire ADC. Okay. Comparator. Have you used the comparator in circuit 1?
No.
Okay. And you know, this is an OpAmp, just a regular OpAmp. These are the terminals, 5 terminals. And if you label this one as VP, this one as VM, does VP equals VM? You have to have a negative feedback in order to make them together, make them equal to each other, and why? I'm going to repeat this again and again until you can answer that question during the interview, all right? Okay, let me give you an example for the inverting topology. So what did you do in circuit 1 lab for you?
We just sold like that. So actually, no, we didn't even do a RF back, I don't think.
We're able to amplify something?
Yeah.
Okay. Yeah. So what are these power supplies?
Just 5 volt DC.
-5 or 0?
0.
Okay.
No, it was just 0.
Okay. And did you tie this one to ground?
Yeah, pretty sure.
So what's the signal here did you put into? Did you use the signal from a function generator?
Yes.
So what is the signal? Do you still remember? Is that it's just an AC signal with offset DC offside, or?
It's just an AC signal.
Okay, no DC offside. So you are not.
I think there was, but I don't remember what we put in.
Okay, so if you put a ground here and ground here, you need a DC offside to lift the signal. Otherwise, for example, this signal swing, there's no DC, right? Yeah. Here's 0 volts, and swing like that, okay? And this already gets into the negative voltage domain. But however, you don't have a negative voltage for the bottom rail. So what's going to happen is whenever you're trying to amplify anything, if you don't amplify anything, but still it's going to be, the bottom will be cut off. But eventually, what's going to happen is the output, right? The output getting amplified, yes, but the negative part is getting cut from the output. You couldn't see anything, okay? But that's something else. I'm going to show you on the next page how you lift it. But now let me ask a question first. It's going to be an interview question, all right? Why these 2 terminals are equal? Yeah, virtual shorted. Why? Why is it virtual shorted? We haven't learned the structure of the OpAmp. You haven't designed an OpAmp, so you probably won't be able to imagine what's going on inside. But when you are learning this symbol, you just need to know what's happening. You don't have to really design an OpAmp. It's, you know, when I was teaching analog, we did an OpAmp design, but not really getting into design. We did lay out an OpAmp. The thing is, whenever you are in the interview, most of the recruiters probably have never laid out the OpAmp. So you don't really have to. You don't have to, unless you are interviewing with the analog design team, just analog IC design team, then probably you need to know the details. Otherwise, you just need to answer the general questions. Just need to know how to use it. That's a bottom line. How to use it, right? So first you need to know why these are equal. So I'm telling you why here. First thing, which is given, right, based on the design of the OpAmp. So the OpAmp has that functionality, which is Vout equals Vp minus Vm times the open loop gain. For an ideal OpAmp, ideally, this is infinite, all right? So this is huge, which means whenever VO, this is a comparator, it's gonna implement this equation perfectly, but here you have a negative feedback, it's gonna be different. So whenever Vp is larger than Vm, no matter how connected, okay? So VO will be this. Okay, keep in mind, that's how this OpAmp is designed. Okay, it's gonna do this equation, operation. Right, if you think about that, whenever Vp is slightly larger than Vm, what's gonna happen here? When Vp is slightly larger than Vm, what's gonna happen here? You will have a tiny positive difference. The subtraction is going to be a positive number, right? And times, for example, 1 million. 100 million. Just give a huge open loop gain there, all right? For example, it's 100 million, okay? And what's the output is going to be here? If it's delta like 1, even though it's only 1 millivolt, what's the result at VO? About 100,000 volts, right? Can you achieve 100,000 volts just by supplying a 5 volts over here? You can if you have a transformer. That's what we did for the summer project on the PCB, what I just patented, right? Just 5 volts everywhere, just 5 volts power supply, but you need a transformer plus voltage multiplier. This OpAmp is not doing that job. Okay, if you have these, then yes. I don't have this, just OpAmp, okay? So the voltage output is going to be limited by the power supply, which is the top rail and bottom rail here. So it's going to saturate which voltage? 5 volts. That's the maximum you can supply. So whenever this is slightly larger than that, it's going to reach that limitation. But before it's reached that limitation, for example, this one will be according to this equation, right? It's going to rise very quickly and becomes a positive voltage. And it's going to feed this voltage back to here. It's going to feed current into this point and to charge it up. Until what? Until when? Until they are equal. There won't be any difference. It won't charge it up anymore, so they are going to be equal. And why this can happen so quickly? It's like a real-time adjustment. Doesn't like here's a bigger than that, then takes 1 hour and feed it back and charge it up. Then they're equal. No, it's a real-time adjustment, very quickly. Happens very quickly. It's like the speed of the electron flows in the circuit in the metal. This is adjusting, always adjusting. Whenever it's a little bit larger than that, equal again. All right. So they are equal because of the negative feedback. Okay. So what if this one is slightly smaller than this one? You're getting a negative voltage here, right? And times the open loop gain, which is huge, and will generate a really large trying to generate really large negative voltage, and will pull charges from this point and to what? To reduce it. Okay, but eventually they are equal again. Because of the, whenever you're answering that question, just make it short. Okay, if someone right now as an interview, someone asks you why, if you have a non-inverting amplifier, why the non-inverting terminal equals the inverting terminal in OpAmp. How do you answer it? Yeah, negative feedback is the first one. What's the second one you want to answer? Infinite open loop gain. Because the difference is the difference times the open loop gain here, which is infinite ideally, even though it's not infinite, but it's also very huge. Even though you just buy a like 50 cents OpAmp, still like a 1 million or something. Okay, so the open loop gain is huge, and so the any differences over here times the open loop gain will generate a huge difference or a very sharp voltage increase or decrease. It's going to charge it up or pull charges out from this point and make it equal. You don't have to say all the things, right? Just directly say negative feedback and the ideal infinite open loop gain of the OpAmp. Just these two will do the job. We'll get you 100 points for that question in the interview, all right? Make sure you know what are these 2 points. I'm going to repeat this throughout the semester. Okay, so here's a question. I want to amplify the signal, right? And I know that the open loop gain is huge. Why not just directly using the open loop gain instead of like put a negative feedback and adjust the gain over here? The open loop gain is very huge. It's very, I can amplify a very small signal, ideally. Why I still bother myself to make all these configurations, the feedback, put a resistor there, and do all the things? Why bother?
Would you overcorrect without it? Because it's so large, would it be overcorrecting the VP and then you get stuck on the
Are close. So whenever you are using that open loop gain over here, you use it as a comparator instead of amplifier. If you are using an amplifier, not all the times you need to amplify the signal by 1,000,000 times. Sometimes you just want to amplify by twice or 3 times or 10 times. And usually you do not amplify it by more than 10, 20 times. Because it also amplifies the DC offset, the noise as well. So you want to amplify like 10 times and filter out the noise and then amplify again. So have multiple stages of OpAmps in real world. Ideally, what's the gain of this one? What's the AC gain? Or voltage gain for this topology? Yeah, VO over VI, right, equals. Yeah. Okay, so ideally if you have 1K here and 1 mega ohm here, you can amplify the signal about 1,000 times. Another interview question, if I just tell you I want to amplify a signal about 1,000 times by 1 stage of OpAmp, can I do that? No. In real world, ideally yes. In real world, no, you never do that. You usually just 10, 20 times. Don't go over that. If you want to amplify by 1,000 times, use multiple stages, right? Do 10 times and filter out the noises 10 times, filter out the noises 10 times. So three times will give you 1,000. Okay? But don't do 1 with 1,000 times gain over here. And another question is why the AC gain is RF over R1? Why is that? There's so many things to cover. And I think I should tell you that, otherwise probably won't be able to learn this anywhere else. So if you do a comparator, so I'm going to get to the signal of the comparator later, but now let's look at this one. Why the AC gain is this? RF, R1, okay. We are just looking at the AC signal. So it's like an AC setup. Oscilloscope, you are not looking at DC. So it's okay to ground them like that. Usually I don't do that. So I have to link this with the VRF, REF. reference voltage to lift it, give a DC voltage, right? But now we only look at the AC signal. If this is 0 volts, this is virtually shorted to ground, right? Why? Yeah. And? Yeah, good. Okay, so my question is, so here's one thing, another very interesting concept. So the OpAmp has a very high input impedance, which means it's blocking any current flows into the OpAmp. So which means after this node, there's no current flows into the OpAmp. Nobody will tell you that, like, why do we still use the OpAmp? That's ridiculous. Like, it's gonna confuse you for 10 years if you don't understand it. So literally, okay, the current flows like this. Nothing get into it. So why do we need it? Why amplify signal? I mean, if the OpAmp is not getting any current, why do we still need it? Right. Okay, so now let's see if we remove it, what's going to happen if we remove it. So VO has to, this is output voltage, it has to do something, right? For example, it's driving a resistive load, RL, okay? Any kind of circuit as a load has an input resistance. So let's just put RL there as a load. It must have a capacitive component as well, like CL, putting them together to model that component. But anyway, it's just a load. And that load must have some input resistance in there, right? And then we look at this circuit. If we do not have this guy, what's going to happen? Nothing, right? And here's a VO, and then here's RL, right? We don't have anything, just a resistor network. Can you amplify the signal, and why? Can you? Is this amplified or decreased? Yeah, it's a voltage divider, right? It's a voltage divider. You won't be able to amplify it. The maximum voltage ideally you can get is VI, somewhere very close to VI. But any other than that, nothing can be larger than VI. It's not amplifying anything. And then, I still don't like the OpAmp, right? Because nothing is getting into it. What this does is just to short this one to ground, virtually short it to ground. So what if we ground it? Still don't use OpAmp. I'm trying to make it very similar to whatever OpAmp does, right? Just short it to ground. Don't virtually, I just short it to ground. What's gonna happen? Why? What's gonna happen? Any voltage difference? Any current?
No.
Be 0 volts forever, right? Yeah. Okay, so now you can see that at least all the other two options just won't work. So why the OpAmp? When we put OpAmp there, it works. No, it's not 0, okay? Don't short it because they're not the same point. Are they? They're not. You cannot short it. It's virtually grounded. It's just 0 volts, but it's not grounded. You got R1, you got R2, RF. What's really happening here? So it just drops VI to 0 volts very rapidly. Okay, and then whatever RF is being set up here it's gonna amplify the current. So whatever current flows through this resistor, and then VO equals I times RF, because this is 0 volts. So VO, or you can say VO is 0 volts minus 0 volts over RF equals I. Because the current is not flowing into the ground, is it? No, they are not the same node. So current is not, you are not losing any current. So still got current flows through here to generate a voltage drop. That's how this VO point here is getting boosted because of the voltage drop. No, because they are not losing current. If you have a zero, if you have a ground, everything is going to flow into the ground, won't bother to go through the resistors. It's like a shortcut. You're going to travel from Colorado Springs to like to where? To Denver, right? You directly drive up. You don't want to go to Vegas and then go to Denver. So all the currents want to go to the shortcut. So whenever you have the current voltage source here, you have these ones, these two, like not virtually, like solid connection between these two nodes to the ground. Then nothing is gonna escape from this node. Everything is just getting to the ground node. All right, but now since they are virtually, they are not really shorted. There's no physical metal short them together, so you are not losing current. So the current are going to flow that way.
But what about the OpAmp? There's current going into the OpAmp.
No.
So
Why it's not getting to the OpAmp? Because, for example, if we have a so the current is not getting to the OpAmp. If you don't part it up, current cannot get into there. So the way it's getting to there is it's being transferred to here, not directly, but by the transfer function. You part it up, then the transfer function is going to convert it to the current flowing here. But this is called the gate, and that's dielectric material. It's a very high impedance. It's not getting into there directly. Okay, so the current flows to the two resistors and generate a voltage drop over here. This is ground, so I times RF will be V out. Because you have a voltage, you have a current. Why you have a current? Because VI minus 0, you have a voltage drop. So you get a current, right? And because of high impedance, the current is not getting to the point, not getting to the OpAmp, so it's going to escape from this node and keep moving to VL. And because I have a current over here, which is going to generate a voltage drop, which is this guy, for VL. So that's going to be VL. So the question is, what is I? You can get I here because VI is given, right? Okay, so what is VL? Just plug I over here. Negative, because when I was doing that, I was assuming current flow that way, right? So I have to have a negative sign over here times RF, and then I move VI over. That's how I derive it. That's a closed loop gain. That's a closed loop gain. Of the non-inverting configuration, which is this. Okay, that's how I derive it. So now you can adjust the voltage gain for this configuration in order to amplify by 10 times, 2 times, 3 times, whatever you want to do. Okay, you can put it here. And there's another name of it. So several names, different names. There's a non-inverting amplifier, or There's another name, it's transimpedance amplifier. Or TIA. Oh. It's everywhere in your life. Mm-hmm. And why it's called transimpedance amplifier? You need to know. Is this a voltage amplifier or current or transimpedance amplifier? Transimpedance, I already told you, right? So it's not a voltage amplifier, and you gotta confuse the game. It amplifies voltage. It's not a voltage amplifier by definition. It's it's called transconductance amplifier or something. Yeah. It's a non-inverting amplifier. You can say it's a non-inverting amplifier or transimpedance amplifier or TIA. Yeah, but by name you couldn't say it's a voltage amplifier because it amplifies current and converts into voltage. That's why it's called transimpedance. It converts current into voltage. And why? You are thinking like, I have a voltage here and voltage getting amplified. Why I'm saying it converts current into voltage. When you derive it, you're looking at the current, not voltage. So the voltage source actually provides a current to the circuit, and the current getting converted into voltage by RF.
So when we do our voltage drop across R1,
Mm-hmm.
is the current increasing there because it's dropping?
There's no increasing or something. It's just like VI over R1. That's the current.
Right.
And because this node is zero, right? That's a voltage drop. That's a resistor. From the Ohm's law, that's a current. Okay. This is just like a current source. Okay. And then whatever here converts the current into the voltage. That's why it's called transimpedance amplifier. And this is everywhere. Everywhere. Give you example. Camera. You don't even need this guy because a photodiode is a current source. You don't even need a resistor here directly. And what is that? That's a pixel. That's to put in the IC, the camera chip, the imager chip, and that's a pixel.
So do they have an OpAmp on every prototype?
No, because it's called, I forgot the name. So for example, here's a physical layout of the pixel, right? It's just one of a million pixels on a camera image sensor, right? And probably the photodiode, you can lay out the diode on a silicon wafer, right? You're going to learn that pretty soon. So you can design the diode on a silicon wafer, on silicon, right? And for example, here's a diode, here's a photodiode, which is this guy, okay? Which senses the light and convert into, it's called photocurrent. Photocurrent. Then what's gonna happen? There's a current source. It's gonna pull current from where? Yeah, it's gonna pull current from here. Whenever it receives the light or photons, it generates photocurrent. And where's the current from? If you disconnect the photodiode, just grab a photodiode, nothing's gonna flow. It probably will generate some charges over here, but nothing's gonna flow, right? Only when you have a circuit, there's a load. you form a circuit so the current charges can flow freely in the circuit. So whenever you put this one in the TIA, whenever it generates charges, it's going to pull photocurrent over here, and what's going to happen? What's going to happen? You got a voltage signal. Depends on the number of photons being received by the photodiode, you are going to have a different voltage level here. And you can convert the voltage level into intensity of the pixel, right? So you can see a monitor here, you couldn't tell, but there are like probably millions of pixels to form each little dot. But this is a display, I'm talking about the camera. Okay, here. Every single pixel senses a little dot and form a different intensity of the voltage signal, right? And then go to ADC, analog to digital converter, convert that analog voltage into like 8-bit, 10-bit, 12-bit of digital signal, right? And then send it to the CPU bit by bit. And it stores it and processes it and send it to the display module so you can see something, right? And when I was talking about that, it's already streamed like millions of pixels over there. That's how that works. It's everywhere. So now tell me, is this a voltage amplifier? No, it's a transimpedance amplifier. Yes, amplifies voltage, but you have to connect a resistor here to form a current. Like it's very similar to a current source. Provide a current and then convert the current to voltage. So SU amplifies the current. So this is a transimpedance amplifier like this one. And it's being used for amplifying photocurrents, not just the photodiode, but also PMTs, all different photosensors, whatever generates photocurrent, it's going to be amplified and converted into voltage, and then ADC. Okay. Whenever you get a digital signal, you can do whatever you want, but it's with the FPGA or any other digital chips. Oh, aspect ratio. I just remember that name. Aspect ratio, which is a footprint. Sorry, aspect ratio, which is the footprint of the photodiode. The ratio of the footprint of the photodiode versus the whole area of the pixel. And you have other things in the pixel like, caps, switches, and other things to form one pixel. So not just the pixel itself, not just the photodiode itself, right? But all the other things as well. If you have a really, really large aspect ratio, which means your photodiode takes a very large area in the pixel, which is a good thing or bad thing. Why? No, it's good. It's just one pixel. You have millions of these ones. It's just one. Why, if you have a big aspect ratio, is better? Yeah, think about that. If you have, okay, I'm talking about a camera sensor. So for example, this is a camera sensor, right? This is whatever the chip layout. You open the cover, you can see a chip. And here's one pixel. Okay, here's one pixel. And here's another pixel. You have many of them to capture image, right? But more pixels is better resolution that have more dots to resolve that image, okay? And so the area, the aspect ratio defines the footprint of the photodiode versus the whole area of the pixel. And if you have a photodiode like that, I'm telling you it's better because only these areas are not sensing photons, so you're not losing too much information. It's like an opening, so the chip has an opening. The chip is pretty much like this size. The image sensors are pretty big, usually larger than the CPUs. Okay, it's an opening on the chip. It's an opening on the chip, and you have lenses in front of it to amplify or focus the image, make an image in front of the photo sensor. Right? It's just many photons are hitting that image sensor, trying to make an image. You can imagine that if you have a lot of areas are just non-relevant, irrelevant things, for example, the caps switches, which are not sensing photons. So the photons are going to hit these areas and not getting sensed. So the quality of the image will be bad. So you need the photodiode area to be a little bit bigger. They are saying like if you have a big photodiode, then it's just 1 pixel, it's pretty big. Sounds like you have a low resolution. No, I'm just talking about 1 pixel. 1 pixel. If you want to increase the resolution, just put more pixels in there. But in the larger aspect ratio. Yeah, because you need other circuits. You cannot just put a photodiode. No. No. So for example, the caps, they are taking spaces on the chip. If you look from the top, they are taking spaces. And these things, all the other circuits cannot block whatever has to happen at the bottom. For example, the caps switches are CMOS transistors. I believe something can be put just right behind it because this is pretty big, right? But not all of them. Like there must be some traces. I mean, because there are so many pixels, you can imagine. Eventually, have to route it, have to send the signal out to somewhere, right? So if you look at, if you have laid out something, you understand why. So the traces takes a lot of space. See, here's the LU. What are these lines? Just wires. So these are the components here. And they're all wires, 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 components, components, wires. Yeah, so wires takes a lot of spaces. Especially when you have so many pixels, it's very difficult to route all these traces. So do need space to run these wires. And answer another question you just asked, right? Do you need 1 TIA for each pixel? And why? Why yes, why not? What you think? I mean, encourage you guys to think, not just directly give me the answer, right? Should I give each pixel a TIA? What's the benefit? What's the downside of it? Take space, so are getting a smaller aspect ratio. So you have a lot of circuits taking the space that do not sense photons at all, right? What's the benefit? It's gonna be faster. It's gonna be faster. So if each one has 1, so you can convert that photocurrent into voltage immediately. But a lot of times you don't need that because it takes time to process all the pixels. So even though you have voltage there ready to be taken out, it's gonna wait there for a while probably. I mean a while probably just like microseconds or something. It's gonna wait there for a while. You don't need that to be that fast. And also it's a huge weakness there is aspect ratio is too small. That's why you don't wanna every single pixel has an OpAmp. But usually how many OpAmps do we have? How many TIAs do we have for the whole image sensor? It's usually just at the very bottom, right? You have 1 for each column. And that's it. So what's happening is you have a row decoder, which is a very simple logic circuit. And you activate each row each time, okay, and send that voltage down to the TIA, no, the current down to the TIA. So actually it's just reading row by row, but doing it very quickly, so it looks like a static image, but actually it's just do it very quickly. There might be some designs has these transimpedance amplifiers inside, but they do need what they definitely cannot do is put an ADC for each pixel. It's going to be a million ADCs for all the image sensors. No, they just have one row here, right? And whenever it's done, right, you activate it and send it to ADC to convert it to digital signal. There must be a lot of registers to handle that, different bits, right? All right, some background for TIAs. But for the amplifier we are going to use for the ADC, it's definitely not a TIA. It's a comparator. So now I understand what's the difference and not getting confused. Because you use a non-inverting amplifier in some other, in circuit 1, for example, and you were taught to use it by giving a negative feedback and amplify a signal and bump it. But now for the ADC we're going to use, it's called a comparator, it's not an amplifier. The comparator is going to follow the same rule. What is that rule here? We just, we just don't care. It's just grounded. So what's going to happen? What's going to happen? Still very useful, right? Even though we don't have a negative feedback. We don't want them to be equal, and they're not equal. Okay. So for example, if we have 5 volts, right? Put 2.5, it's 50% of the full range over here. And I'm gonna varying this voltage. Here's VREF or VM, right? 2.5 volts here. Okay, and VP, I'm just doing a DC sweep. Here's 5. Just explore all the voltage linearly. Okay? And what is V out? So what V out looks like. Yeah, and it's going to saturate the V out. So this amplifier or a comparator, even though it's not ideal, but this one is still very close to 1 million, for example. Okay. Whenever VP is slightly larger than VM, when VP, this is VP, right? Okay, when VP, here's VM. If you zoom in, you can see that whenever VP going up is slightly larger than VM, what's going to happen? Shoot to 5 volts very quickly. Why? Because you have a very large open loop gain. The open loop is not closed loop. You have a huge open loop gain here. But because you don't have 1,000 volts, it's going to reach 5 volts very quickly. It's going to reach to 5 volts really quickly. And whenever VP is larger than VM, it's going to maintain that. Until VP is slightly smaller than VM, it's going to pull it to where? To 0, because you don't have negative voltage. This is the lowest voltage you can supply. It's going to saturate at 0 volts. It's actually cutting off the signal, but we intentionally do that. It's not like this, it's cutting it off, but we like it. We are using that kind of property here. And whenever it's larger than that, let's do that. I don't think you can maintain that. Any other noise, anything, any noise. Oh, if they're short together, you got nothing. Yeah. I remember the name of it. When you short them together, there's still a current. I forgot the name, but there's a current flowing through it and amplify a little bit. So there will be a little bit DC offside voltage, but tiny. You're not using that topology for any reason. So the comparator is going to do this. Okay. Why is it called comparator? It compares these two nodes, which is large, and flip this voltage to indicate which one is larger. Okay. Whenever this is 1, which is larger? Yeah. If VL is 0, VM is larger. Okay, so it's comparing these two nodes. That's why it's called comparator. Let's do something like let you guys to know. All right, so one question here. Still, let's come back to this inverting topology to make sure you guys know what's happening here. Okay, no, I'm not supplying a negative voltage. Another question, why is not negative voltage? Why in the labs, if I'm doing this lab, I usually do not supply a negative voltage to it. Why? It's not really easy to generate negative voltage on one PCB board. Not really practical. You can see all the lab instructions, right? All the lab instructions. They're telling you how to use OpAmp, right? Make this connection. Then you can ground it. Okay? It's gonna work fine. It's okay because of that. So now I have a swing range and a ground everything here. So our DC offset is 0 volts. So you can freely swing in this range, which is fine. Okay? Is that practical to do this? It's okay to do in the lab. It's super convenient. You have to make a negative voltage, and you remember how to do it with the 2 power supplies. No. Mm-hmm. Mm. Ah. That clear? So the question is, which is 5, which is negative 5, and why? Yeah, why? Yeah, this is known, this is given. Dropped by 5 volts, got negative 5. Boosted by 5 volts, got positive 5, right? That clear? If you have 2 power supplies, this is how you do it. To generate this voltage and supply to here, it works really fine. No problem. Okay, but if you have a circuit, you're designing amplifier for a sensor on the PCB board. A lot of times you don't want to do that. Yeah. Yeah. Whereas there are many ways to bump it up, right? Does that make sense? So now that's the bottom rail. And you are not allowing your signal swinging around 0, but you lift it. So you can swing like that. Okay. Because the virtuals are virtually shorted, whatever voltage here, for example, we got 2.5, it's going to appear here as a DC offside. Then what? The superposition. You put a DC, you put an AC. So it's lifting that AC to the DC level. Superposition. Okay? You superimpose that DC voltage to the AC to lift it. So very practical point of view here, right? For example, there's some kind of sensor. I don't care about what's the sensor is being used for, but it's a sensor outputting a millivolts level signal. PMDS or thermocouple voltage signal. Okay. The signal you could, so from the sensor you couldn't control it because the DC offset can be anywhere. Like that. And here's the power supply. Here's ground. And that's a signal output from the sensor. I'm trying to directly feed it into an amplifier. Let's just do it that way. What's going to happen? I have that whole range to amplify, to swing it, right? But now it's not ideal in the middle. It's swinging around something like 1.1 volt or something. If I amplify it, what's going to happen? Yeah, no, DC is not being amplified. So what's happening here? So it's like, yeah, so it's, for example, it's being amplified like, yeah, the DC is amplified or not? That's right, that's true. Yeah, because the signal is only inputting, getting to one node, and there's nothing here. So it's going to be the DC, for example, the differential is being amplified here, and AC amplified like that, then being cut off over here, right? So usually if you have a sensor output like that, what's the first thing you want to do? Sensor output signal, so you want to remove the DC offset first. High pass. So after that, everything is down to the ground. And then lifted. Superposition. Provide a DC voltage here. Okay, you can lift it to here. And then do that thing. So the question is, should this be ground or VRF? VRF. So the DC, there's no DC difference, no DC offset difference. It's a differential amplifier minus to each other is going to be 0. So DC offset is not being amplified, right? But only AC is being amplified. So always, if you're dealing with a sensor, do high pass filter first, remove the unknown DC offset, and then boost it or lift it by the desired DC offset, which is half range of the full voltage, to amplify it. So after that, probably the signal is not perfectly swinging around 2.5. It's probably gonna swinging here because of the noises, 2.8 or something, right? And you want to amplify this guy further. So for the, if you have a second stage of amplification, you're gonna do high pass filter again, remove whatever DC offset being generated over here, remove it, and then force it to be VRF, and then just do it again.
If you know your signal won't be amplified, like it won't be amplified out of your range, could instead of putting a high pass filter in between each one, you just put a high pass filter at the beginning and then at the end of all of your amplifications if you know it won't?
Because you have noise amplified here as well. It's the undesired DC offset being amplified. They are not ideal OpAmps, so there will be some DC difference here, which will be amplified. That's why you don't want to amplify the signal immediately to a very high gain, because of that. 10 times, you got decent signal and remove the offset, and do it again. Very practical. So we design a axiometer. Pronounce, I forgot. Come back to here. So what we did was a oximeter, how to pronounce it. It's the same IR sensor like you used for the robot car. Done, pretty much done. Yeah, done, pretty much done. Yeah. Yeah, put your finger on it, it's gonna flow, it's gonna sense the oxygen in your bloodstream on the fingertip and convert into voltage. And that's a signal with, everyone has a different DC offset. Have to remove and boost it, remove it, boost it, and amplify it. Eventually, you show it in the oscilloscope, right? Something really practical. And then Arduino, you can see your heart rate over here. All right.